that's the second rejection. No, like all in all.
Yeah. Overall.
That's what counts. Huh. So we would like to challenge problem number 5, dynamically oscillator. Okay, can we go to the next page? Another rejection. Okay, that's the last 4-3 rejection.
It was the 5.
Sorry, third rejection. Oh, third rejection by problem number 5. Problem number 5.
Yeah.
Yes. We would like to challenge problem number 2, ready this. It's called hold the rounds.
The presentation.
I just because like I wasn't able to teach all the just for this round. So like, I know you are experienced, but no, again, it's not that much. We would like to challenge problem number 6 in a small tower. Okay, problem number 6 is acceptable. You have 5 minutes for preparation.
Nice.
Okay, so guys, calm down. The recorder seems to be ready.
Hello, my name is Patrick Pesci, and I welcome you to my presentation about this year's 6th Iypt program called Tennis Ball Towers. This program requires us to build a tower by 20 stacking tennis balls, 3 per layer and 1 on top, and investigate the structural properties and limits of such tower. Also, it asks us to look at what happens if more than 3 balls per layers are used. Now, let's get into the theory, but before that, we will discuss a few necessary variables and definitions. Firstly, the gravitational force, G will mean the gravitational force, S will mean the frictional forces, N will mark normal forces between the balls, mu will mark the static frictional coefficients, and F, X, Y, and Z will mark the X, Y, and Z components of forces in a 3-dimensional coordinate system. Also, by definition, one level of a tower will mean 1 layer of 3 tennis balls, and also we will include the top ball as well. So, firstly, let's see how the forces go in a simple tower, in the simplest cases. So, the tower is held together by the static frictions. For a simple 2-level tower, we don't need any kind of special 3-dimensional coordinate systems. We only need a 2D projection from above, where the red dots will represent the centers of the walls, and from that we can calculate the sine of set alpha. After that, we write down an equation for the horizontal forces. The sum of their sum should be equal to 0 for the tower to keep stable. And the sum of the vertical forces also has to be 0. Now, and the sum of the terms for the tower to be stable must be 0 as well. So, we will use the axis that goes to the center of the ping ball, and from that we get that the two frictional forces acting there must be equal. Now, after solving these equations, we get that the normal forces between the walls will be G divided by 3. Here below that we can see the the frictional forces, and after that we see the minimum necessary frictional coefficient between the balls and between the balls and ground to keep such tower stable. Now, let's look at what happens if the balls are not touching each other in such a simple case. Now, let D be the distance between the balls on the layers, and let's define K as a dimensionless variable, where this D is divided by the real use of the balls. In this case, this K will have to be less than the value there, because otherwise the middle ball would just fall into. And now, the cosine of the previous mentioned alpha can be seen there, and from that we can calculate the normal forces between the balls will still have to be G divided by 3. Then we get more complex formula for the frictional forces. From that, we can get a formula for the minimal necessary frictional coefficient between the walls and between the walls and the ground. Now, from this, we get this really interesting graphs for the minimal necessary frictional forces between the walls depending on the value of K. As we can see, it approaches 1, which means that if we have higher frictional coefficient, it is actually capable of holding really widespread towers like this. And here we can see when it's stable or unstable. This is what I meant. The way that the frictional coefficient are measured will be introduced later. Now let's look at how we expand our theory for higher level towers. First, we build an equation system in a three-dimensional coordinate system where we define each coordinate. Now, the normal forces, frictional forces will have an x, y, and z components. And of course, for the tower to keep equilibrium, we need that the sum of the x, y, and z components of each forces must be 0. Here we can see the equation for one of the walls for the x components. And of course, the sum of the terms around every axis must be 0 as well. For convenience purposes, we will choose the x, y, and z axis of our coordinate system. Also, the color, it's enough for us now to write down these equations for the common color balls because of symmetry. Now, after that, using direction vectors, we are capable of calculating the necessary frictional coefficient for such towers. So, for example, for the three-level tower, for all towers, we get that the necessary frictional coefficient between the top wall and the wall below that will have to be 1.41, and this is true for every tower. And as for this three-level tower, the other necessary frictional coefficients can be seen there. Also, this system of writing down equations is really versatile, since we can just add new forces for our equations and see what happens. For example, like a pushing force from the top, which is like having a higher mass for the tower. Now, let's look at what we use for our measurements. So first we have made a force measuring gadget by adjusting, by sort of putting together an adjustable pull and push device and a force measuring device. After that, to measure friction, we have fixated a ball for our force measuring gadget. Then we have made the ball capable of rotation. And after that, by putting these two devices together, we could measure the necessary frictional coefficient in the walls by measuring how much force is required to move the bottom wall. From this, we get really interesting graphs. What we see here is that actually the static frictional coefficient can be defined as a line. It depends on the compressive forces. What we see is actually at lower regions, that at higher compressive force, the static frictional coefficients will need to be higher, and also the green dots represent lower friction walls. And with those walls, it wasn't even possible to build a tower like this. Now, let's look at our setup for other stability measurements. First, we looked at the carrying capacity of such towers. Now, we used our previously mentioned device and pushed the tower from the top. Now, what we see here is the maximum carrying capacity for the two-level towers. This can be done, we calculated analytically. We get this equation out there, and what we see is as the force from the top approaches infinity, the necessary frictional coefficient at the bottom approaches this 0.31 value. This is between the walls and the ground. Now, we have done measurements with different surfaces. And here we can see these results. What we see here is that after at 0.31, we have an asymptote of the function, and above that, theoretically, we assume that the balls are perfectly spherical. They should be able to withstand an infinite amount of force. In our case, they could withstand more than 50 newtons, because that was the highest we could measure. Now, let's look at the structures when they are higher level towers are put under this carrying capacity test. What we see here is that the three-level towers actually has a significantly higher carrying capacity withstanding ability than the lower towers. But to have these measurements correctly, we had to introduce a kind of construction error to have a distance between the balls as the levels increase to get the reasonable results. Now, let's look at what is the force withstanding capability at non-zero distances between the balls. So, for a two-level tower, we get this complicated equation, but after plugging it in, depending on the value of k and the maximum force needed, we get such a graph. Now, let's look at what happens if we are not pressing the top wall, but we are applying force from the side. So, firstly, we have examined two types of this type of measurements. There is type 1, which is not level dependent, and type 2, which is also not level dependent, because what we see is that actually the ball below the top wall just falls out. Now, for this we get these results from our theory and measurements. What is really interesting is that here the our theoretical result is significantly lower than our measured values. We can say that this is true because the pushes were not perfectly straight, and when they are not perfectly straight, what we see is that it starts to polarate to the type 1 measurement and gets closer to that. Now, we have also done so-called acceleration test. Here we, in our theory, gave a fixed acceleration to all the balls and then computed our measurements numerically. Now, what we see here is that through our measurements we got these results and those are numbers. Now, what you see is that at type 2 the theoretical value is actually higher than what we have measured for its capability to withstand. But I believe that it's because of the construction error and the differences in the balls. So let's look at what happens at other towers at other widths. So firstly, I have calculated the necessary frictional coefficients between the balls for such towers to be stable. Now here we can see that depending on the tower level and the balls used per layer, we see the necessary mixed frictional coefficient within the balls. Now at balls per layer when it equals 6, I wrote undefined, since in that case a tower can be built. Now, let's look at the maximum carrying capacity of these other towers. On one layer there are 4 and then on one layer there are 5. So we used two-level towers here and the number of balls on the bottom layer depending on the maximum force that they could withstand. And that's what you can see here. Now, in summary throughout my presentation, I have talked about the physics of a simple basic tower. After that, I have introduced a theory for a more complex equation system, which we can use to calculate the parameters of higher level towers. Then, after that, I have made measurements for friction and stability. After that, we have compared this with our theories, and then we made a few more extra measurements, and we have also looked into other cases that are asked by the problem. And thank you for your attention. Correct. So the limit of the towers that I have built is actually, I have only built the towers that are, which are level 6, but it theoretically should be higher, not higher.
I'll move to the next question.
Alright, okay.
Okay, so do you measure the variance of the radius and your mass of your tennis balls?
Well, I didn't vary the mass and the radius, but in our theory they are not dependent.
So you can measure the variance between your tennis balls.
Oh, sorry, I have
and how many different types of tennis balls did you use?
For most of our measurements we use the same type of
Okay,
tennis balls.
and next question I want to ask, when does the tennis ball start to collapse? Where does this structure start to collapse?
Oh, of course. So it depends on the type. It depends.
And you mentioned in your theory that how it collapse, the coefficient of friction is 1.41 for all the layer of tower, right?
Yes, it is.
Okay. And you mentioned that.
Sorry, but the maximum coefficient of collapse, but the maximum, the frictional coefficient of the tower
Yeah,
could be for it to be stable. Yes.
Yeah. So to get a horizontal push and you do vertical push, so you can see that your data that is over magnitude, the data.
Sorry.
Like the force that you push vertically and horizontally is over magnitude. So do you know how to explain this?
Yes, basically this is let's say an angle tower measurement method.
Okay, so just ask you that is the tower more stable? Is the tower more easy with horizontal disturbances, right? It's more sensitive to horizontal.
It emphasizes one on the top, right?
Yeah.
Yeah, exactly. Yes.
Okay, so next question I want to ask.
I'm sorry, you have to keep it for the discussion. Thank you very much. Time for question.
Ready? Please start.
Good afternoon, I'm Untitled Chapter from Team Taiwan. Today I'll be opposing tennis ball tower number 6. Okay, so for the report overview, firstly they did observation of necessary static friction 2D for equilibrium, and they did a coefficient of friction increases with the distance. And for the pros, their setup can efficiently remove the gaps between the bolts, and they didn't mention the top there, but they didn't mention that the top there is the weakest thing. And there are no pictures or videos that mention a high structure, which they said is 6 layers in my short questions. And secondly, for the ball model, they use force equations, and but they didn't calculate the force required for on top. And for the pros, they did mention that the coefficient of friction needed is 1.41, but the cons is they didn't mention the required coefficient on top of the 3 layers is the same, and they didn't find the recursive relationship for n-layer tower, which I mentioned later in the discussion. And then they did an experiment on top force, which is a vertical one, and they did a static friction and compressive force graph. And they found maximum value, which the vertical force is on the three-layer tower. And we think that they analyzed the stability of the top by applying vertical force, but they didn't mention the ball variance and the mass. And they didn't explain why the stability when force vertically that would decrease with the tower layer. When instead of they exerted sliding force to the tennis ball tower, and they find maximum value, and the deviation is because the position is not straight. Okay, so the process that they did horizontal disturbance. So we think that the horizontal disturbance is why the tennis ball structure cannot be stacked to like infinite layer of tower, because you mentioned in your report that any tower needed a 1.41 coefficient to be built, right? So there shouldn't be no limit to this tower structure. And the cause is the pushing horizontally should be done, but without much trouble, and it is not a relevant thing. And they didn't mention the ball variances, and they did not explain why the layer tower can withstand better horizontal pressure. And third, that they did the experiment with different balls per layer, which is what the problem statement told us to do. And the process is that they mentioned the 4 and 5 per layer tower, they're unstable. And the deck of data, and they didn't mention the contacting between balls that makes the 3 per layer tower more stable. Okay, so first discussing point, first I want to discuss the point of failure, which is why the tennis ball tower starts to collapse, which is the point that it starts to collapse. And I want to discuss the horizontal disturbance and the vertical disturbances, and why the differences is over a magnitude. And then I want to discuss the direction of friction between layers, since they only theoretically model, they only calculated the force on the top layer, which I think it is more relatively easy to do because of the symmetric on the top layer. So I want to discuss this also, and I want to discuss the deviation that caused by ball types due to error propagation. And for the experiment, okay, and I want to discuss why the ball structure can make tennis ball that exceeds coefficient of 1. I want to also mention the importance of coefficient of friction in this experiment. Okay.
Okay, thank you very much. Please start the discussion.
Okay, so first. Okay.
So firstly, thank you for your invitation.
Yeah. Okay, so first I want to ask. So I asked you in a short question, and you said that the tower collapses. So if I have a tennis ball tower, and you said that it will collapse randomly, right?
No, I didn't say that it collapses randomly, but so you are trying to ask me where does it collapse?
Yeah.
Okay. So.
Oh no, I want to ask you the point of collapse. Where does the structure start to break?
I mean, like what force or what point?
Yeah, I want to ask which layer, like the top layer or the bottom?
Yes. So as you can see here, I have calculated it for these towers that I put up. So first, this tower where the distance is 0 and there are 2 levels. If the frictional coefficient is low enough, it collapses at the bottom. Then this one collapses at that layer, and this one also.
So then you calculated the coefficient of friction needed for the tower over here?
Well, in our complexity. Yeah, it is calculated, but in our calculation system we implemented it a way that we just calculated when it reaches that.
So can you turn to page
Of course.
12?
12.
Page 12. I think that you mentioned that, no,
Before.
I think the things you mentioned that they needed 1.41.
Yeah. Okay.
So 1.41 is very uncommon for coefficient of friction, right?
Indeed, it
Because
is.
So you know why the tennis ball structure can exceed 1.41?
Well, as I will explain it, it's because of the surface of this tennis balls.
So one thing that is because of the bumpy surface of the tennis ball that the bumpiness of the surface of the tennis ball can intertwine with each other.
Yes, indeed. So it's because of the further surface of this tennis ball that they are intertwining each other. And after this is the reason why we get that special graph for the frictional forces. At the smaller compressive forces, they are intertwining with each other, they are keeping each other touched, but it's hard to pull them apart because of these knots. But at higher compressive forces, this becomes less and less relevant and more of the normal
So
friction.
you're saying that the pressure can cause
Indeed, I'm saying that it can, the what you see here causes that.
It is this thing, right?
Can you see
Compressive
that?
force. So since the first layer has the highest coefficient of friction needed, like 1.4, this is very high, right? So
Yes.
it should be the point of collapse. So
Interestingly,
and it's also conclude that the top layer is the point that the tennis ball structure collapsed. Do you agree with me?
no, I don't agree. Let me show you something. It's in my just a second. But wait, you can.
Okay, but what we discussed more interesting, that the coefficient of friction increases with the vertical force.
Yes, as the vertical force increases from the top, the necessary frictional coefficient for the tower to be kept stable at the top actually decreases from square root of 2, special graph as you can see down.
Yeah,
Yes,
so this is very interesting because
indeed it
the
is.
physical structure looks like there are 3 and only one on top, right? So the pressure on the first layer is only one ball, and your pushing force one is the unit for this.
That's newtons. So it's newtons, yeah.
So like one tennis ball is like 60 grams. So your pushing force is like over here. So it is basically still 1.4.
About yes.
Yeah, still. So I still cannot agree with you that the tennis ball structure collapses from bottom because collapses from bottom. Can agree with me on that.
It's not collapsing from the
Yeah, because
bottom.
we already said that tennis ball structure can have a coefficient of 1.1 due to 1 series, right?
Indeed, it can
Yeah,
happen,
so,
yes.
so if you can stand the first power not practical so the whole part can withstand 1.41.
Well, not the whole. So maybe the bottom of the tower is unable to withstand, but the top can definitely withstand because of the compressive force to frictional coefficients relationships.
So so for the first discussion, we think that the point of failure, which is falling from the first structure and it's falling from the first layer of the tennis ball structure. And I think you did horizontal pushes and vertical one, right?
Yes, I
Do
do.
the horizontal one.
Oh.
First come to the vertical one to discuss one more characteristic about tennis ball. Come to the vertical one.
The vertical
is vertical push is 19, yeah.
Okay. This one.
Yeah, so you can see that 2 is
Indeed.
very small, right? And 3 is boom. And
It's
4
boom.
and 5 is 6. So
Indeed.
you don't have to explain this.
Well, simply it's because we made these measurements on a kite surface. No. But I mean, it's measurements, but basically the two-level tower is really dependent on the surface it is on.
Video showing you did this experiment.
The higher level tower collapse?
No, I mean the vertical experiment. Do you have a video showing?
Yes.
Okay, so let's look at this video, and you can see that. Oh, okay, you can see that. Okay, start on the video. You can see that when you give a vertical force, you can see that there's gaps starting to form.
So here the vertical force starts, and what we see is that it increases, no gaps.
And you can see gaps starting to form. Okay, so this
Okay,
is Okay, I want to discuss another thing about tennis ball. So can you touch the tennis ball? You can feel that there's a soft belt on here, right?
Obvious.
Yes,
Yes.
there's a small belt. So it could. So there's a slipping, and so you know the slipping between the balls. But we think that the gap form doesn't because of slipping. It is because the smooth belt over here starts to deforms. So it will form the gap over here.
Yes, sorry, but indeed, it forms the gaps. But what we have measured.
So
but what we have measured is the maximum force that it can withstand. And when the gaps are formed, the maximum force is that they can withstand gets lower.
Yeah.
So it that's one shows the maximum forces.
The means that the gas form can lead to bigger horizontal disturbance to the tower. The bigger horizontal component will
Like if you put it for both apart from each other, it can withstand less force. It's true. It's definitely
back to page 19.
19.
So it is because that the gaps are formed,
Yeah.
the horizontal component of the force becomes bigger, so the force and back power decreases. Yeah, so this is how you
That's why I have introduced the kind of construction error variable, which is I would say is increasing as the
next
you can go on.
discuss the horizontal pressure. You do this.
horizontal.
Yeah, so you can see that horizontal. Yeah.
No, sorry.
But the previous one, so you can see that the value over here is relatively small.
Yeah, here.
So this is the true thing that causes the tennis ball tower to collapse.
The horizontal.
It's a true reason because if you think that this tower collapsed due to the big vertical push, but the only vertical push that's pushing the tower is the top wall, which is 60 grams, right? So it is not logical. So the thing that causes the stability of the tower must be the horizontal push.
So here, are you talking about these measurements?
Yeah. So so can you agree with me that horizontal push is the thing that causes the
I mean, obviously the tower is pushed from above and the balls will push apart from each other horizontally as well. But the main force that we are acting from the outside is the push from above. I can agree that there is horizontal forces and they cause it.
But since you can only build your tower with 6 layers, right? So
sorry, I could build it for higher layers, but that was the amount of walls we had and measurements.
the reason for that. I want to discuss why the reason that you can only build the 6 layer of
No, so you should be able to build higher towers.
Oh, you should be because it is 1.41 for every tower.
And on the top.
Yeah. So we think that the variance involved means a key factor, and you can use the error propagation, which means that you can imagine that the tower sits on the plane and goes on top, right? So if you have a variance in one layer, that is a slight radius and mass, slight variance in radius, you will cause uneven surface, right?
But uneven surfaces are
Yeah, so if one model is this and the other is a little bit bigger, so you will cause the surface to
okay, yeah, I understand.
Yeah,
so and indeed it can increase, but as I've said for our measurements and theory, we kind of could neglect that. Yeah.
So the incline of the plane will cause horizontal pressure, which is more sensitive to pencil card experiments.
Okay, thank you very much. Hands up.
So first in my discussion, I discussed that the point of failure of the tower is on the top plane because it needed the highest contribution of 1.41. And then I discussed the importance of the characteristic of tennis ball, such as the bumpy surface that can cause 1.41 coefficient of friction, and the belt that can compress, that can be deformed, and it will cause a crash on horizontal pressure that would lead to the deviation in case of vertical experiments. Because the horizontal, the vertical push indeed is 1.41, right? So it should be the same value, but it will drop down. And I also discussed the variance in balls will cause horizontal push, which is more sensitive in this data. And I could explain why the report can only build a tower to number 6 layer of tower this way. So I really had a great discussion with the reporter, and I thank you for your kind attention.
Thank you much. Questions from the reviewer?
First of all, I'd like you to plug in your presentation. The first question is, in what condition were the balls and were they all the same?
Okay, so the walls were mostly the same. We had about 1% difference in the radius, or maybe something bigger than that, but their mass and their size of radius is higher, the more mostly, they are the same. I think they could be considered the same.
As we can see here, it's like 21, some of them seem to be rough up.
Indeed, sorry.
Therefore, can you prove that the friction coefficient is held constant for all the balls in all places?
Yeah, so they were marked because we have measured the frictional coefficients separates for multiple balls, and so they were there because we have measured the frictional coefficient for multiple balls, and we haven't seen big differences.
The next question also to you, the acceleration test and your sideways force test. Did you try different angles when applying the sideways force and the acceleration?
No, the angles that were tried were in my presentation.
So you didn't try different angles? Is that
Those two angles. Yeah. So I didn't try other angles.
Question for you. Do you think that trying different angles would have made a difference when testing the acceleration or the sideways force?
Yeah, you would cause horizontal pressure, horizontal force, which is at least to the depth of the tower.
Next question to the reporter. What is the role of the top ball exactly?
Well, the role of the football is to hold all of the tower together, and it basically provides, because of its low mass, enough friction. So not even for its own mass, it holds the tower together. I mean, that's the role.
Would you have the same view on the role of the top ball or a different one?
So the top ball needs to have a bigger coefficient of 1.41. So if you try with the big ball, it may not exceed that value, so it cannot be a higher structure.
Then could you stick to slide 7?
7, yeah, of course.
Yeah, you mentioned the balls ball distance. You mentioned that the difference, as the difference changes, you have to change the frictional coefficient. What do you mean by the distance?
But this is the previously mentioned K value, that is the distance between the balls divided by the radius. This is for a two-level tower. This happens because from the equation we get that the pressing force between the balls will have to be G divided by 3. It doesn't not depending on the distance. And if you think about it, due to symmetry, if the frictional forces are in a 90 degree with the normal forces, then if the tower is basically flat, then to have the double up, we need at least a friction coefficient of 1.
Okay, I'm sorry. Time's up. Thank you very much. Time for your question. Many times after preparation, please start your review.
review problem number 6, tennis ball tower. I think we're all familiar with the problem statement at this point, which is why I would like to see this being reported first. So some of the positives of the report were that there was a first analysis done of the tennis ball tower and
Louder.
and of the equilibrium and the static reaction. He analyzed for 2 and multiple layers, and the required static friction was analyzed. However, some negatives were also found in the theory. For example, unclear variables were used as he changed from mu to c in the middle of the report. No theoretical limits were explored, and no qualitative or quantitative definition of stability was really given. Also, he did not define a standardized tennis ball, and no investigation of the layer, of the top layer of importance and the role it plays was done. In terms of experiments, some of the positives were that the tower consisting of 3 tennis balls per layer was conducted. There were good friction determination setups, and the carrying capacity, also including side pushes and acceleration tests, were done. However, the error bars were not always clear. No error analysis was done, since the number of tests was not specified on. The problem statement explicitly states that only 3 balls per layer have to be used, although some other structures were also used. The structural limits of the experiment were not really considered. Varying friction was not considered. There were insufficient experiments for higher towers, so exceeding 5 levels. And also, different angles were tested in the sideways force test or the acceleration test, which in our opinion would have been very interesting to see. Now let's move on to the opponent. He made very relevant questions in his question phase, like questions about the limits of the theory, limits of experiments, so how many layers are possible with a structure like this, and about the unclear dimensions of the standardized tennis ball. He pointed out a lack of data of towers exceeding a height of 5 levels during his speech then, and he also mentioned missing analysis of the role the top ball plays in this structure. He, however, did have some unclear and scientifically inaccurate, let's say, formulations, like without too much trouble, which we didn't quite understand what he meant by this. And in our opinion, he spent too much time on very few discussion topics, which could have been spent discussing way more pressing matters. Now let's go on to the discussion. First of all, the first point was about the collapsing point. The opponent asked about the collapsing point and where the tower actually does collapse. The reporter stated that it collapses at lower levels, and we agree with the reporter that lower layers are certainly more fragile in this structure. The next point was about the slipping of balls. The opponent asked if gaps formed during deformation. The reporter said that they didn't. And we actually agree with the reporter, since gaps can form because there are always 6 contact points per layer. Therefore, gaps cannot form. The last points of discussion were about the angles. The opponent said that the test of different angles would have been important, and the reporter said that this did not seem as relevant to him. And we agree with the opponent, a more rigid testing of the stability of the structure, especially taking into consideration different angles from which the side force or acceleration is to be exerted, would have been very interesting and very informative to see, as we would have gotten a more rigid view of how the stability of the tower stretches across its whole structure. Thank you very much for your attention.
Thank you. Concluding remarks of the report.
Okay, so firstly, both the reviewer and the opposition talked about the deformation of the walls, but as they deform, as the gaps are formed and angles are formed, it is true that they are formed, but what we have investigated was the maximum force carrying capacity, which is not dependent on that, since when they are formed, the tower can withstand less forces. So I think it was a misunderstanding in what we have measured. Now, during our discussion, I think the reporter asked about the parameters of our balls as we used and how they were different. Now here, what we can see are the parameters of our balls. which were measured. Now, of course, there is a slight deviation in the radiuses and masses, but it's about 1 or 2 grams and less than 1 millimeter, or more, about 1 millimeter in radius, which is actually could be considered to be one of the limitations of our theory, that we didn't assume that. But as you can see, even with that, we were able to do decent predictions. Now, it was also mentioned what is the highest tower that we could build, and that I couldn't show a picture. So here is the picture of our 6th level tower. So I have said if there is a frictional coefficient larger than the square root of 2, then it should be possible to build even higher level towers. But of course, the top goal must be able to provide that. During our discussion, the error analysis and in the review, the error analysis of the accelerations were also brought up. Basically, how we did the measurements is that we made the measurements multiple times in an acceleration range, which we didn't know about, and after that, I have analyzed it. And of course, the angles are. We have examined at least 2 possible angles, and thank you for your attention.
Okay, thank you much. Questions from the jury members? Anyone have a question? Okay, yeah.
Okay, so I have a question to the reporter, which is a follow-up to like the original discussion. You talked about the friction, friction when these surfaces get intertwined. So did you include the friction in the theory as a normal friction or just some additional force?
We included in our theory in a way that at certain regions we assumed higher frictional coefficients according to not this one, but okay, so we have included it in a way that at most forces the frictional coefficients actually were lower because higher forces were acting, but at other parts, for example, when the top wall was pushed, we actually had to calculate with the highest friction we have measured, because of course the forces there were really small, the compressive forces were small.
Thank you.
Thank you. Nicola.
I have a question to the reporter. Well, did you build some model predicting the highest possible power? How many layers is the highest possible power?
But in our model, so we have only a theoretical model. Our theoretical model is capable to describing all the towers to high levels, but since it's in our model is numerical, we haven't built a perfect theory for that. But what we can say is that if the friction coefficients are higher than what I have mentioned before, then actually, and if the surface frictional coefficient is high enough, then theoretically it should be able to satisfy.
And please go to slide 37. 37, the next one. And the previous one. The top wall there looks like it's different to the other walls in terms of the surface structure.
That's
shorter fibers.
Yeah, so is a different wall, but we have made multiple measurements and compared each other, and what we have seen is that there is no real difference. The fact we have used it.
I have two quick questions to the reviewer. So, did I got it correctly? So you were complaining that they used more than 3 balls because it was not in the task. Am I right?
He spent some time discussing a structure which was not in the problem statement.
Okay, but the problem statement said what happens if we use more power. Am I right?
Well, in that case, you would be.
Okay, and the second quick question was that did you say that gaps cannot form?
Well, since if you consider that every ball.
Because like we have seen a movie here where apparently some gaps form. So like how does
the balls deform, but still theoretically you should always have 6 contact points between the balls, which is why if gaps form, the ball should in theory collapse. Which is why I don't think that's true necessarily.
Okay.
Well, when you show the friction of the rods like 15, you have like lower friction balls, so that those are.
Yes, so the difference is that actually, as you could see, we use rough balls for most of the towers. There's a new, okay.
Wait, let me ask my question first. You measured friction coefficient for one ball?
No, for all the numbers. So that's the reason they got number.
How did you assign coefficient friction to just one ball? Even you measure all of them, but how did you assign to one ball?
So I have made multiple measurements for the balls, and what I saw is that it's not really relevant, that they are not that much different, so I assigned the same one for all of the
Sorry, I
balls.
just make quick what you said. The differences between the balls are not relevant.
Okay.
Yeah.
Okay, sorry, I have one. You have this resulting coefficient friction somewhere. There is a slide. So can you show me the slide? Like that, you had a minimal friction for next layers and minimum friction for one layer. No,
So
not experimental. A theoretical calculation. You compare that.
Which approach is one?
Yeah.
Which approach is one?
No, yeah.
This one?
No, the one before. There was a number saying like, yeah, okay. So the CD number, like where this exactly comes from, this value 1.1.
Okay, so it comes from the structure. So we assume that
So it's a calculation.
it's a calculation.
So like approximately, it's just in this.
No, because it's a longer number, so obviously, yeah.
Okay. And answer.
Then all your towers always stay up under these parameters.
If the frictional coefficients are high enough and the other
If you
basically,
tell me
yes.
a tower like this, it stay up.
Yes, if you build it well, if you build it perfectly, with
Right.
perfect walls, then yes, it does.
So if you align this line, it's like
Okay, Alice, sorry.
Thank you for the questions.
Okay, thank you. Georgi, time's up. Okay, so we need some time to finalize this. Okay, just while we are waiting on the jury out of curiosity, the coefficient of friction between tennis balls is something which is like highly non-trivial thing because I've done for a company with a group of colleagues like measurements for a company which is producing not tennis balls but like balls for sports which is called paddle, which is basically a tennis ball just filled inside of something, and they've asked us to perform like professional measurements of the coefficient friction and the dependence on the load and the friction between different rockets and different coatings of the rockets, and it's like it's science. It's not like just like a fraction of friction, and it's just not one number, and it's like it's really complicated. So as you can see here, it's like what you are taught in the school that you have friction, which is normal force times a number which is constant throughout like all the range of parameters. Like in the reality, like if you are playing a smash, it's pretty much different coefficient of friction than if you're playing in wires. Okay. Did you sum up, Javier? If you are really under troubles that we do it that way, that like the break is separate. We have done it in the past. That's look. Students have break while we give points and while they prepare we have breaks. But this we are not that uncertain. Okay, ready everyone?
Yes.
Okay, grades for the report. Now 6, 7, 6, 7, 6. Grades for the opponent. Now 6, 9, 8, 6, 6. So you didn't turn up. And grade for the review. Now it's 5, 6, 6, 6, 5. Wow. This was smooth. This was smooth, no? You understood you have to explain a lot if there is a big spread, so okay, anyway, Georgi wants to say something.
Yes, I still have to say something. High grade for opposition and the report, I think, so yeah. Also.
Okay, like I would still like two people very briefly comment the report so that we get some feedback. So as you started, you can hit on the higher side, so
It
7.
was clear that we had done many things, but you got lucky for my high grade because like during the report we were so fast and I was with like 100% paying attention and at the end my head almost exploded. But it was due to the opponent in the discussion. He also managed to just discuss a lot of things and like in the discussion I saw many aspects of the report to which also I liked and that's why I gave the high points. Maybe I could have
Okay,
if like the report was more like organized.
partial points.
3.75 plus 2 minus 0 is 7.
Okay, it's 6.5, so you rounded up.
6.75.
Okay, Nicola? 6?
Yes, I would like to say some things about the report. So generally, I really like it because I realize that this problem is really hard. So maybe I expected to see a little bit more about the situation when you have gaps between the balls and they are not that defined, but I did not. Well, maybe I wanted to see a little bit more about the agreement, the comparison between theory and experiment, and most of all, I wanted to see a prediction of the highest possible power using prolonged model.
Okay, for the opponent, yeah, you already started about your 9, this was really high comparing to the others.
Yeah, clarifying question was not that it was like normal and they broke average, but it was not like really nice, but the discussion I liked it very much. Again, you kept the fast pace of the reporter, which was not very comfortable for me because like again I had to work with full capacity and I was afraid that I would like miss something because I would get tired, but still I managed to like, and you discussed like the whole variety of things, you showed that what was the report lacking and like the major things that could have not been understood during the presentation, you like understood it from the study.
Yeah, I like the fact that you asked clarifying questions, resolving some unclear points. I think that was very good. I think you got most of the main points in the talk. Time management, I think you looked like you were going to say a few more things and you ran out of time. So I think that was a little bit underserved. And I think that the discussion was held in a very good spirit. It was a discussion. It wasn't two people trying to shout each other down. So I appreciated that.
But you are on the lower side.
It was on the lower side.
Yes.
Really? Wow. So my passing scores were 1, 2, 1.75, and that adds up to 5.75, so rounding up to a 6.
Okay, and you can continue because you also had a 6 model reviewer, which was on the higher side.
Yeah, I also thought, so the review, I went up and down a little bit for the review questions. I think the questions were well spread between the reporter and the opponent. You used your time well. One or two things I think had a very good first question. My first question would also been all the balls identical because the surface area doesn't look the same. And so I think that was a very good question. You mentioned that they didn't say anything about the standard tennis ball, but the problem doesn't ask for anything about the standard tennis ball. So I think what they presented in terms of the size of the ball, the average frictional force and so on was sufficient. And I think that was...
Okay, but now you are on the higher side.
Yeah.
Okay, anyway, and the partial rate?
1.5 for the questions, 1.5 for the missed points pointed out.
Okay, my side on the 5. So I gave you 1.25, 1.8, because I was in the legal position, I didn't particularly like it, and especially I didn't really score well for you for the discussion. It was just 0.5 because basically like point by point I didn't agree with you, and then also I didn't like you made a few categorical statements. I just couldn't agree. There was like a statement about 3 balls, which is like clearly not reflecting the. This means, come on guys, if you review the problem, you should talk about the problem. And also like the gaps cannot form like we have seen, like you have seen it here. So you need to tell this kind of categorical
I got something also for the reviewer. The thing of the angle with acceleration is something that you ask them and you stated it like a discussion point. So it's not the same. You ask them, they were not discussing it, they have not the arguments made and look at as a discussion point. I think it was not.
Yeah, that's nothing like technically it's a review. Okay, very briefly.
For the review, I also agree with Martin. I also gave a -1 point for that because, but in general, like initially, I liked the review and the construction of it because you calmed down the stage a little bit and outlined like everything calmly. So I could relaxingly enjoy and sum up everything in my head, which is like what reviewers should do, and also just you.
Yeah, the start was good, and then you completely unnecessary. Like you had paint that were not correct. They were very clear, and they were not.
General comments to the reporter. So I wrote quite a high grades, and I think in this method we got lucky because of the fact that this problem was submitted my supervisor, so I was familiar with this problem. But I didn't write high grades because of that. I was familiar because of this problem, and I got many things during your presentation and discussion. But otherwise, you were very fast, and if I was not very familiar with the problem, I would not have get anything, and I would have gone much lower. So if I don't get anything, then yeah, I think.
Okay. That's 10 minutes break.